52 is another one of those classic magnetic field problems. It wants to know the magnetic field at this point right here because of this wire, this bent wire that's around it. So there's some current traveling through a straight section around this loop, down a straight section, back around this loop, and so it goes, complete circuit like that. What is the magnetic field at this point? So a couple things to begin with, and hopefully you can start recognizing this fairly quickly here. In this particular wire here, the eye is to the right, and the way you get to the observation point through some r, which is what the Biot-Savart law calls for here, is through a sort of a distance like that, a little r right there. So if you look at it, the I is to the right, the r is to the right. That tells me that the angle between I and r is 0 degrees. And the Biot-Savart law includes the sine of that angle, so the sine of 0 is equal to 0. This wire doesn't contribute any magnetic field to this field point. That's the first point there. Another way you can think about it, a little wire segment like this is going to have these magnetic field lines sort of circulating around it like that. According to the right-hand rule, this way it'll be circulating up out of the page, back around like that, and back in again. But the wire sort of ends abruptly right there, so other than some residual fringing field, which we don't count for in this textbook or in these problems here, there's no contribution because of the current in this wire at this point right here. And a similar thing is going to happen over here. Yeah, the current's going to be to the right in this case here. I is going to be that way. But in order to get back to the field point here, you'd go back through a distance r like that. So I is to the right, r has to go back to the left, but that's an angle of 180 degrees between them. The Biot-Savart law has that sine of 180 in there, but the sine of 180 is also 0. So you get no contribution to this wire either. So nothing from that one, nothing to this one. You can also think of this one here as the magnetic field circulating around these points here like that. According to the right-hand rule, the wire ends right there, so it won't contribute anything to those points. So what you're left with then is what contribution does this semicircle and this semicircle make at this point here. You can get that fairly straightforward in that we have a result for a circle. The result for a circle, right at the center of the circle here, is mu naught I over 2r. Now this would be the magnetic field if you had a full circle of current going around the magnetic field right there at the center. So as you might guess, the magnetic field due to half of a circle, which is what you have here and here, is half of this result. You can do the integral yourself, or you can just use this here. So I'll say b to the half circle of the semicircle is mu naught I over 4r. So you can use that result to solve this problem here, because what do you have? You have the superposition field due to two semicircles in this case here. So the way I would write this here, I would say something like, if this is semicircle 1 and this is semicircle 2 here, of radius r1 and r2 here, you could do something like this. You could say that the magnetic field due to semicircle 1 there, that it contributes to this point here, is mu naught I over 4r1. And likewise, you can say the magnetic field that's contributed by the bigger semicircle 2 there is mu naught I over 4r2. So you have the magnitudes right there. The only thing you sort of need to figure out now is what would the directions be. Well, if I put my thumb in the direction of the current on this big semicircle out here and curl around, I'd get a magnetic field contribution up pointing right at me because of the larger semicircle. So I'll draw a big vector like that and say this is B1 out here coming right at me. Now for 2 here, 2's going around like this. I put my thumb in the direction of its current and curl around like that. The contribution due to that smaller semicircle is actually into the page, right on top of B1. So I'll just go ahead and put this on here. Another semicircle right on top, and that's B2 here. So B1 is pointing out of the page, but B2 is pointing into the page. So when you go find your superposition field here are your magnitudes right here, but the question is, do you add them or subtract them? Well, we'll say B1 is positive, pointing up this way. We'll say B1 is negative like that. So for this particular problem here, the B total is definitely going to be B2, the magnetic field due to this bigger coil coming at me, minus B1, the smaller field going down in like that. So there is a bit of cancellation like that right there at the center of the hoop there. And that's the way you get that problem solved.